Alright, hey guys, this is Wednesday, April 22nd for geometry. We're on the last section here, 13.7. Again, if you need any help as we're moving through this, get up with me. I can help you out through some of it individually together. And so 13.7 deals with the golden ratio and other applications of similarity. So again, you're taking the actual math on the board and applying it to application and things like that, to world type deal. And so the golden ratio, just going to read some here because this is basically just definitional stuff. The work isn't actually too complicated. And so it says an interesting phenomenon appears often in art and sculpture of the ancient world. In many of Michelangelo's and Leonardo da Vinci's paintings, a special rectangle ratio occurs. The ratio is called the golden ratio. The golden ratio is the ratio of the length to the width of a golden rectangle. A golden rectangle is a rectangle with the following characteristic. If a square unit is cut from the end of the rectangle, then the resulting rectangle has the same length to width ratio as the original rectangle. And figure 13.19 approximates it. And so notice, basically what happens is you're essentially, they just have to match the ratios. And so however we have the box, however we have the original box, when you cut it, the ratio of the big box to the ratios of these two smaller boxes have to match. So they have, that ratio has to match. Then when we cut it again, the ratio of this third box has to match the ratio of the big box and the other two boxes, and so forth and so on. So they have to be proportionate. They don't have to be the exact, they're obviously not going to be the exact same measurements, but they have to be proportionate to each other. And so that's basically how that's done. If you look at the figure there in the book, it kind of shows you the details of that and shows the general rule. One neat thing, if you look on page 572, it says the golden spiral is an important application of similar figures. Look at the golden spiral shown. The spiral continues to form smaller and smaller rectangles, but in the proportion that is shown, you should see 5 golden rectangles because their sides are proportional. All these golden rectangles are similar. What is the common ratio that shows all the rectangles in proportion? God included the golden ratio in the design of His creation. You can observe the golden ratio in the spiral of a nautilus shell and the whorls of a pineapple. There are many other applications of similarity too. You've already seen how surveyors use similar triangles and things like that. And so the idea is, basically what happens is, if you do the, I'll just illustrate it real quick again. You have this and this and this, and then it basically divides it like that. Basically, if you start, what happens is it does a spiral. And so if you look at it on, do they actually give you one with the spiral? Don't know why they didn't show you the actual spiral. But basically, it just spirals to where it gets smaller here, and it just kind of does the spiral. So if you look at a nautilus shell, it's kind of cool because it actually does the spiral where it's looking like this, and basically it actually does the proportion out of the golden rectangle with the nautilus shell. And so that's basically just shows you how in nature these things kind of happen naturally. One thing I want to kind of hit on with y'all, just because it's what I enjoy with it, you have what's called the Fibonacci sequence. And the Fibonacci sequence is basically was delivered by a guy named Leonardo Fibonacci. And basically, there's a rabbit problem, which basically says if you started with 2 rabbits, and the rabbits basically wanted to see how many the population of rabbits increased, then you would have one rabbit. Then if they both had a baby, then that means you would have 3 rabbits. Or 2 rabbits, my bad. And then if these 2 had a rabbit, then it would go to 3. And basically the Fibonacci sequence just expands it to where it's a recursive sequence, where basically you're adding the prior 2 terms. So 1 and 1 would give you 2, Then if you had 2 and 1, that'll give you 3, 3 and 2 will give you 5, 5 and 3 will give you 8, 8 and 5 will give you 13, and basically expands like that. If you do want to look up the rabbit problem, it is an interesting thought process. Google that, the rabbit problem with the Fibonacci sequence, and I'll go into more detail. But basically the idea here is that here's the Fibonacci sequence. The cool thing with this, and this is just cool how math works, the Fibonacci sequence is actually going to approximate the golden ratio. So the more terms you get out here, the closer it's going to approximate it. And so what happens is that, where am I at? Does it talk about the ratio? Yeah, it says that if you compare the lengths of the rectangles to the width, you get a ratio of 1.619. And so that's the ratio for the golden ratio for the golden rectangles here. So what happens is the more of the Fibonacci sequence you do, the closer it's going to approximate that. See, if you did 2 divided by 1, you have 2. Then you're going to do 3 divided by 2, 5 divided by 3, 8 divided by 5, 13 divided by 8. And the more you go down the line and do that, it's going to get closer and closer and closer and closer to the golden ratio. And so that's just a neat math thing for me that I enjoy looking at. But basically that was on top of the lesson. Basically all you're doing for your actual lesson is just giving the ratios. And so if you have the ruler, like on number 1, it just says for each pair of photographs, find the scale factor of the dilation that would produce the second photograph. And so basically you just are measuring one side of the rectangle, and then the big rectangle, and then measuring that same side of the smaller rectangle, and then that'll be your fraction. Same thing for 2, for 3, same thing for 4. Number 5, 7, 9, 6, 8, 10, all those, basically you're doing the same thing. Only it says look at the series of rectangles, find the ratio of length to width. So now instead of doing the ratio from one box to another box, you're doing the ratio of length to width. So you would measure the length and then divide that by the width. And so that would give you your ratio. So you would measure the length, divide that by the width. And so that would give you your ratio. The next ones are just some thinking problems basically. So like 11, 12, 13 onward. Just kind of think through those. They're just applicational ones. But basically, again, you're just setting up your fraction, and that's pretty much it. And then you're just kind of thinking about what they're giving you there on those last few. And so if you have a ruler, do those. If you don't have the ruler, as long as you understand the concept, I'm fine. But make sure we understand how to do the ratio of length to width. All right, hope you all have a good day.